Let's talk about drones. Let's imagine we have a drone and it's in a construction site and it needs to fly through and take pictures at various positions in the construction site. You can imagine there's a lot of different paths the drone could take. For example, it could start at this objective and go around the map in this way, or it could start at this direction at this objective and go towards the bottom of the map and then come back up. Not all of these paths are equal. Some might have longer distances to travel, and others might be more dangerous. They might get closer to the obstacles that we want to avoid. So picking a path is an important challenge when you're working with many different types of robots. Now, here I'm actually going to show you an example path that is pretty reasonable. This green dot here is the obstacle we have, and you can see that the drone is actually going to fly to the right first, go through these obstacles, and then go to the bottom of the map and come back up. This is a pretty reasonable, efficient path. So let's let the drone take off and start following this path, and I'll tell you a little bit about how we implemented this. I'm actually going to start by showing you one of our unit tests. So we made a library to do this mapping, and you can see an example of how to use it here in terms of how to set the geometry of the map. So this takes in how far you want to stay away from the obstacles. It takes in the resolution of the map. We represent the map actually as a series of cells, like on a grid, and it takes in the X, Y, and Z span of the map. You can add obstacles to the map, which is important because we want to avoid crashes, and you can add objectives to the map, which is useful to be able to solve for paths that visit all the objectives. Here's an example of how you might use our library to get a path through all the different objectives. So this then gives you the path. And we are actually using ROS2 and AeroStack to control the drone. So we actually need to expose a ROS2 interface from our mapping server to the drone. And this is that interface definition I'm showing you here. So this drone is actually flying on the path. The AeroStack controller talked to our library to get the path. And you can actually see it's approaching all the different viewpoints, and it's going to try and take different pictures of them. And as it's doing that, it will capture the picture, it'll remember it in memory, and then it will move on. So what this looks like at the end of all of this is it'll put together a composite image of all of the different images that it captured along its trajectory to show that it was in fact successful. Now, I mentioned there's a lot of different ways you could choose paths. There's a lot of different paths. We implemented a couple ways to choose among them. One way is this combination approach that simply looks at every possible path and picks the best one. Now, you can imagine as the number of objectives increases, the runtime of this, which we're looking at in the top, explodes. And this is because there's a relationship of n factorial between the number of objectives and the runtime in this algorithm. Now, another algorithm we implemented is the nearest neighbor approach. So this actually takes a heuristic, which says, hey, pick the closest, start somewhere, pick the closest objective, and then repeat. Go to that objective, pick the closest objective. You can see that this scales much better with the number of objectives, but this actually comes at a cost. It also chooses suboptimal paths. So in the bottom here, we can see that this objectives 11, it found a path with 72 meters long, where the optimal one was 63 meters long. So in engineering, many things come at a cost, and we have to pick and evaluate these trade-offs depending on our domain and our problem. Thank you very much for your time.